In order to approach these problems, you have to start by making the graph. In this case, I thought it was easiest to take a look at the narrative here and turn it into a series of data points that I could then plot on the graph. And in doing so, we get a result that looks sort of like this, where one of the runners is moving at a sort of fast speed and then slowing down, and the other runner is moving at a consistent faster speed, even though she starts a bit later. The first question asks, if the race were to go to 35 meters, who would win, based on the assumption that they continue at the pace that they're at. 35 meters, is somewhere up here on the graph, and even, by the 30-meter mark, it's pretty clear that Sylvia has gone further than Andy in that same amount of time. So after 15 seconds, Sylvia already has a lead. That lead looks to be increasing over time, so we would say Sylvie is the likely winner if the race were to 35 meters. The position that they meet is the location where the graphs intersect. So they are at the same position at the time of about 12.5 seconds, and that position is about 22.5 meters, and I just got that by looking at where that line intersects on the graph. If your number looks a little different than that, that's okay, as long as you understand the approach. Question 3 asks about the difference in their position at time 7 seconds. In other words, how far ahead is one runner versus the other at the 7-second mark. If you look at the time 7 seconds is right here. For both runners, they're at very different positions, and it's the space between the graphs here that tells you exactly how far apart they were. One of them was at 6 meters, the other one was at 17 meters, so the difference was 11. So there was an 11-meter lead by Andy at this point in the race, but as you can see, that lead is decreasing because Sylvia is running faster than Andy at that point in time. Then question 4 asks you for the average velocity for each runner, the time interval 0 to 10 seconds. So between 0 and 10 seconds, what is the average velocity? To calculate this is just total displacement over time. We're not interested in pathways or how they got there. We simply want to know at the 10-second mark, how far did they get? So looking at Andy's curve, he is at about 20 meters in 10 seconds, which gives him an average velocity of 2 meters per second. Over that same period of time, mostly because she wasn't moving for the first 5 seconds, Sylvia has only traveled to the 15-meter mark. She's right here. So her average velocity at that point in time is 15 over 10, or 1.5 meters per second. You're going to graph this one pretty much the same way as before. Look at the narrative that's provided to you, use that to create a t-chart, and then use your XY coordinates to plot out the velocity versus time graph. Our first analysis question asks you to figure out what is the acceleration over the last 5 seconds. On a velocity time graph, that's a slope. So if you look at the last 5 seconds, that's this section right here. We're going from 8 down to 0 meters per second, so that's a rise of -8, and we're going from 25 to 30 seconds, so the run is 5 seconds. So -8 divided by 5 gives you the acceleration, -1.5 meters per second squared. The next couple of questions ask for average velocities. To do average velocities, we need displacement, and on a graph like this, we need to figure out the area underneath the curve. So the first question, too, asks you to figure out the average velocity for the entire trip. We really can't do that without first answering question number 4, which is how far the car went on the trip. So this is kind of a complicated shape, so I broke it up into some simpler ones. I had one triangle here that has a height of 20, a base of 10, so 1/2 base times height gives me 100 meters of displacement. I had a big rectangle in the middle that is 10 by 20 for a total of 200 meters. And then I have a triangle, and the top here, a rectangle here, and a triangle down here. And for each of these I made the calculations. For this one here, looks like a height of 12, a base of 3, and it's a triangle, so we cut that in half. Down below here, it's 8 by 5, and again it's a triangle, so cut it in half. Then this rectangle here is 8 by 5. So I took all of those individual displacements and added them up to get a total displacement of 378 meters. I divided that by the total time of the trip, which is 30 seconds, to get an average velocity of 12.6 meters per second for question 2. Question 3 asks a similar question but over a different interval. This is interested in the average velocity from 8 to 12 seconds. So we're looking at average velocity from 8 to 12, which is the total displacement divided by the total time. The total time is easy to figure out. It's just 12 minus 8 or 4 seconds here. The displacement we figure out by doing another area under the curve, only this time just between 8 and 12 seconds. So I think the easiest way to do that is to split this up into 3 shapes. You have down here a large rectangle that's 4 seconds wide by 16 meters tall, which gives you 64 meters of displacement. And you have 2 shapes up here, a triangle that's 2 by 4, and again times 1/2 because it's triangle, gives you 4 meters. And then this rectangle here, which is 4 by 2 again, but this time it's the whole rectangle. You don't have to multiply by 1/2, so you get 8. So there's 8 plus 4 over here plus 64 over here. It gives me a displacement of 76 meters in that 4 seconds. So the average velocity in just that time is 19 meters per second, quite a bit faster than the average for the whole trip. We've already answered question 4. It was really part of question 2, so those are out of order. I apologize for that. But 378 meters, we already know, is the total displacement based on the area under the entire curve that we did back in question 2. And then lastly, 5 asks you if there's a point where the car goes backward. It does not. If this was a position time graph, you'd be looking at forward, rest, and then backward. But as a velocity representation, this is all forward motion. It's all velocity in the positive direction. So you are speeding up as you go up this incline, and then at a constant velocity for a few seconds, then slowing down, then constant, and then slowing down again. So at the end of the trip here, we're at rest. We've stopped moving, but we've been going forward the whole time. So imagine it's like riding a car where you speed up and cruise for a while, then you slow down because you enter into a school zone or something, cruise for a while, then come to a stop at a stop sign or at your destination or whatever. All the while you're still going forward, but you're speeding up and slowing down. That's what's represented here. If this graph were to have continued down into the negatives, that's how we would represent backward motion on a velocity time graph.